Hi, good morning. Can you hear me?
Yes, ma'am. Good morning.
Yeah, thanks for attending. I wanted to prepone the session because of personal reasons. But anyway, since the meeting is being recorded, I hope things should be fine.
No issue, ma'am. Ma'am, one thing.
Mm-hmm.
I think previous recording sessions are not uploaded in YouTube.
Oh, is it? I told the team even yesterday. I told them. Maybe I'll remind him again today. Okay, so he'll be uploading it. I guess today. I informed the team yesterday. So how many recordings are not uploaded?
I
Hello.
think, ma'am, only two recording sessions are uploaded.
Oh, only two are uploaded. Okay, I will after today's session. I will inform the team. At any cost, they'll upload it by 11 a.m. today. Okay, because your exam is also coming up tomorrow, right?
Yes, ma'am.
Yeah. Or let me just check with the team right away. Give me a minute. I'll call the team right away. Okay. Hello.
Yes, ma'am.
Really sorry, guys. It's the confusion with the team. I'm going to report this issue. The team is not doing it on time. I anyways told them in another 30 minutes the recording should be available in your portal. Okay. If not, please email me. Okay. Otherwise, I don't know. If you don't get any recordings or anything, please email me so that I can talk to the team. Okay.
Okay, ma'am.
Yeah, so I was thinking that the team uploaded. I didn't know that the team did not upload because I'm sending them the recordings and I'm asking them to upload. So it's the mistake from their side. If you don't receive any content on time, please let me know. Okay, I'll talk to the team.
Now, ma'am, I can see the lectures are uploaded. I think.
Lectures are uploaded. Okay, all right.
Yes,
Yeah,
ma'am.
but this is like a serious thing. I sent them long back, and tomorrow is your exam. You can't receive the recordings only today, right? So if you don't receive them on time, please let me know. Okay, I'll talk to them. Right. So we can start with today's thing. So the plan, at least I thought for today, since like I'm planning to sit for 2 hours, 8 to 10 am. I'm really sorry for preponing it. So I'll quickly, in 30 minutes, I'll give some introduction to week 5 because that assignment is also pending, right? I'll give some quick introduction to week 5 and then we can discuss about your quiz doubts. Will that be okay?
Yes, ma'am.
Yeah, all right.
Ma'am, you have said that you will show some MATLAB examples.
Hello. Yeah, Subhash, you were telling something. Sorry, I'm talking to the team.
Ma'am, actually, you have said that you will show some MATLAB examples in the past.
Sir, okay, MATLAB examples. You mean the proper coding MATLABs? You
Yeah, yeah,
want some demo on that? I can
yeah,
do that after your quiz is
yeah,
done, okay?
yeah.
Maybe so this week, what I'll do is I'll give this quick introduction to week 5. Uh, so there are less topics only in week 5. So we will do week 5 topics now. And next Wednesday, I can do this MATLAB demo. Will that be helpful?
Yeah, ma'am.
Okay, so this convolution and all, I can show you how you can do it in MATLAB. Okay,
Yeah, ma'am.
right. So I'll just give the quick introduction, 30 minutes, and then we can discuss your quiz related doubts. Okay.
Yeah, ma'am. Ma'am, so,
So, yeah.
one second. So, signal processing means that everything what we are studying right now.
Signal processing means, yeah, exactly. Whatever we are studying right now is known as signal processing. Apart from this, there is more to signal processing. There are a lot of other varied topics: audio signal processing, video signal processing, digital signal processing. So DSP is a separate course. Signals and systems followed by there is a higher level course known as digital signal processing. So there are more to it, like you learn more about filters, other kinds of transforms, and other kinds of system blocks, like sampler. All those things you will see in digital signal processing, which you don't see here in the signals and systems course. This is the basic course for signal processing. Okay, once you learn these tools, like there are, like other higher courses like digital signal processing, multi-rate digital signal processing. There are more like the courses are more deeper than what you're studying now. Okay,
Okay.
yeah, all right. So, I yeah. So the week 5 topics. Till now we saw signals. Till week 4 we saw signals. What did we see in signals? We saw what exactly a signal is, and we saw like how to time shift and scale a signal. And we also saw the properties of signals like even symmetry, odd symmetry, and so on. We also saw the periodicity of signals, whether the signal is periodic or aperiodic or anything. We saw such properties of signals. And we also saw the topic of phasors. Phasors is like every complex. So all these properties are for real signals. So we have phasors or complex valued signals, both are equivalent. And in this case, we saw other properties like conjugate, symmetric, conjugate, asymmetric, and all. And what else did we see? So more or less, like these are the topics that we saw till date, right? So till week 1 to 4. Now, once you learn these things, now we are going into the systems. So systems are like, a system is something that takes in one signal and produces out another signal. So one signal we represent by x of t and the other signal we represent by y of t. And x of t is known as the input signal and y of t is known as the output signal. And some standard systems that at least professor taught in your class are, so this, let me define this system. So this is a system. Let me call this system or denote this system by F. So some standard systems that we saw in your class are, integrator is a system, because what does an integrator do? So an integrator takes in the input signal x of t, integrates it, and then produces the output signal y of t. How do you write this y of t? So y of t, if I call this signal as f, y of t is that f applied over x of t. And how does that look? So it looks something like this, x of tau d tau. So integrator is a system. Likewise, differentiator is also a system. Okay, so these are some standard systems that we see in our regular lives. And what other systems are there? Any system? Suppose amplifier. Amplifier is like, it amplifies the amplitude. Suppose, so where do we use this amplifier? Suppose you are not able to hear something. Suppose when you are watching a TV, and if you are not able to hear something, what do? You will increase your volume. In place, the sound signal is being amplified. So what does that mean? Suppose if your signal strength is like this, x of t and t, you're amplifying the amplitude. In place, you just amplify the same signal, you amplify. So suppose here the amplitude is a, you're amplifying the amplitude by 10a. So even amplifiers are systems. Okay, so you have an amplifier. Suppose your original signal is a times x of t, amplifier produces out 10a times x of t. This is your y of t. Okay. So yeah, all such things which takes in some signal and does something over the signal and produces out, all such boxes or doubles are called as systems. Okay. So yeah, so that is what we are going to study in the rest of this course. So we see how these signals are being processed in systems and what kind of operations can these systems do to the signals. All those things we will study. Okay. And yeah, the main topics that were discussed in uh, uh, week 5 topics are as follows. So systems can be divided into multiple. So systems, all systems has several properties. So based on the property that it satisfies, they can be divided into several systems. uh, One such thing is causal system. So we will see what a causal system is. And other thing, memory or memoryless systems. So based on the property they satisfy, they are called, based using such names. So if you are given any system, like for example, if you are given a differentiator, and if you're asked to say like what kind of system is this, so you verify all these properties and you can write down several things over here that telling that the differentiator is a causal system, the differentiator is a memoryless system, the differentiator is a linear system. So all these are properties, for this particular system. So why do we need these properties? These properties will be really helpful in analyzing the systems in your later parts of the course. So we'll study all those properties in week 5. So we have memory, memoryless systems, invertible systems. Okay. We have stable systems, and we have time invariant systems. We have linear systems, Any system that is linear and time invariant is called as an LTI system. Okay, linear time invariant system. Okay, and we also in week 5 we also saw an important property known as convolution. So convolution is a very, very important property. At the end of like week 5 summary, I'll go through this convolution thing in detail, and we can also look the convolution property in more detail using MATLAB examples in the next live session. Okay, maybe Wednesday. So what I'll do is I'll quickly summarize how you can, so given a system, how you can figure out if the system is a causal, like how you can quickly identify these properties. Okay, we'll go through certain examples. I think professor gave enough examples in the course, but anyways, I'll go through certain examples so it is clear to you guys and you can solve your assignment problems. Once this is done, we can discuss your quiz topics. So please feel free to stop me if I'm going, like at any point if you're not able to get it. Okay, so yes, so first one is the causal system. What is a causal system? So we call a system to be causal, okay, if output, which we denote by y of t, output signal at time t depends only on the input at time t. Or earlier. Okay, so if the output signal y of t, it depends only on time t, the input at time t. So if y of t is some combination of input at time t or some combination of input that exists in the past, that exists in the past, so that exists in the past, then such a signal is known as what? Causal system. So here in this example, suppose if you take y of 0, it is equal to x of 0 plus a times x of, let me take capital T as 1, x of minus 1. So y of 0 depends only on x of 0 and x of minus 1, which are the past inputs. Okay, so or if you take for that matter any t, y of 1 is x of 1 plus a times 1 minus x of 1 minus 1, a times x of 0. So these are either the current level input or the past input. So it is not depending on the any future input. Suppose if you take y of t is equal to x of t plus x of t plus t, same t equal to 1, then y of 0, if you see, it depends on x of 0 plus x of 1. So output at 0 is depending on the input at the time instant which is in the future. Hence this is not a causal system, but this is a causal system because the output depends only on the present level input and the past level input, but not on the future level input. All such systems are known as causal systems. So causal system means output at any time t depends only on the input at time t or the earlier version of the input, but not on the future version of the input. Okay, so all such examples, so y of t is x of t plus x of t minus 1 by 2. Can someone say if this is a causal system or not causal system?
Yeah, causal system.
So y of t is equal to x of minus t by 2. Can someone say if this is causal or not causal?
Yeah, it's a causal.
Why is it causal?
It only depends upon the past.
That's not true, right?
Yeah.
So if you take negative t, suppose your t is less than 0, take minus 1. So y of minus 1 is x of 1 by 2, which is depending on the future. So this is x of 0.5. Output at minus 1 is depending on the future value of the input. So this is not a causal system, right? Even if, disagrees the property for if it disagrees the property for at least one value of t, we say such a system as non-causal system. So here in this example, for all t less than 0, this is the case. The output depends on the future values of the input. So this is not a causal system. So for a causal system, for every t, it should satisfy the property that the output depends only on the present or the earlier versions of the input, but not on the future. That should be agreed for every value of t. If it disagrees for even one value of t, then we say that it is known as a non-causal system. Okay, so here in this example, this is a non-causal system. Okay, so let me give another example. So y of t is equal to x of at, a not equal to 1. What happens to this? Hello?
Yeah.
Is
Whatever.
this, yeah, y? So if you take a to be equal to 2, y of 1 is equal to x of 2, depending on the future values of input. So this is not a causal system. Okay. One final example with respect to causality. So y of t plus t is equal to x of t. T is something that is greater than 0. What happens to this?
Yeah, it's a causal system.
Why? So how can you prove it is a causal system?
So in output, when we are substituting some time,
Yeah.
it will
So
be the input as some past.
yeah, or we also know that you know how to go back from this. So y of t is simply x of t minus t, right? And all output values at any time t depends only on the past values, right? So hence this is a causal system. Okay, so y of t is x of t minus t, or in other words you can say y of t is the delayed version of x of t. So since it is a delayed version, whatever you're seeing at present, you know it's the delayed version of the input, so it might have already appeared in the past. Okay, so that's the idea. So this is a causal system. Couple of more examples. Y of t, so this is something that was already discussed in your class, I guess. Is this a causal or non-causal? Differentiator, and let us also take integrator. Are these two signals causal or non-causal signals?
Causal.
So this is causal. This is also causal. Why? Differentiator, if you see, y of t is differentiating the signal only at time t. It is only depending on the input at time t. Hence, this is a causal system. Likewise, if you look at y of t, the integration is like what? In continuous time, integration is like summation in the discrete time, right? So if you have a discrete signal, you represent it as integrator, you can represent it as minus infinity to t x of n. So these two are equivalent. So this is in continuous time and this is in discrete time. I mean, if the given signals are discrete, you represent the integration like this. And what is happening if you see, you are integrating over x of tau such that the range is from minus infinity to t. So at any time t, you are integrating until only time t. Okay, so the output is not depending on the future values of the input. Hence, this is causal. But if you're given something like this, can you say if this is causal or non-causal?
Non-causal.
Yes. Why? Because the output is also depending on the future values of input. You are integrating the time axis until 3t, which is depending on the future values of the input. Hence, this is non-causal. Okay. So I hope these examples are clear. So causal system is something where the output at time t depends only on the input at time t or the earlier version of the input, but not on the future. If at all at any time t, if the output is depending on the input, uh, future input, then definitely that is a non-causal system. Okay, so this is with respect to the causality. The next one is memory and memoryless systems. So causal, we have seen that output. So in causal, we have seen output depends on present and past, no future. Okay, so this is causal, right? But for memoryless, output depends only on present, no future, no past. Okay, so again, considering the same examples, y of t is dx of t by dt. Is this memory system or memoryless system? Hello?
Memoryless.
Yeah, this is memoryless. Likewise, y of t is integral minus infinity to t x of tau d tau. Memoryless or memory?
Memories.
So likewise, y of t is equal to a times x of t. Memory or memoryless?
Memoryless.
More confusing, y of t is square root t times x of t.
Memoryless.
So memoryless, let me denote by ticks, and memory I am denoting by y of t is t plus 1 by 2 times x of t.
Ma'am,
Mm.
why differentiator is memoryless?
Which one?
First one.
Differentiator. So differentiator, if you look at it, y of t is, you're differentiating the signal only at time t. It depends only on the present value of the input, not anywhere else. Hence, that is the reason why it is memoryless. But whereas if you look at the integrated system, it is going from minus infinity to t x of tau d tau. You need all past values of the input in order to integrate this. So you are integrating, suppose if your signal is like this, differentiator you are doing at this point, right? Or if you look at the integrator, you are integrating it from this point until here. So you're looking at the area under the integrator. Hence, that is this is a memory system. I think I'm telling it clear. Let me just see my. I think I'm telling it giving the right answer. Maybe just to ensure, let me just. Yeah, I think it is correct. Um, Hello.
Yeah.
Okay, so I'll verify that anyways. But yeah, this is correct. I think. I mean, there's nothing to this. It only depends on the present value of the input. Hence, it is a memoryless system. That is all it is there to it. Or for your case, let me just re-verify it so that I'm not telling any mistakes. Well, yeah, this is a memoryless system. Yeah. Okay. So this is how you see memory or memoryless. So if the output depends only on the present, not on future, not on past, then we call such a system as memoryless system. If at all at any point t, if your output is depending either on the past or on the future, then definitely we call such a system as memory. Okay. Memory implies, like, in order to find the output at y of t, you need to know some you need to know some value of the input at what input in the past. So if that is happening, then that that implies you are saving the input somewhere, which is taking some memory. Or if your output depends only on the present value but not either on the past or on the future, then we call such systems as memoryless systems. Okay. I'll check this, but at least as far as I remember, this is a memoryless system. But I'll check that and I'll let you know, guys. But for now, I'm proceeding with the next things. Did professor talk anything about this in your class?
What about the last system? Y of t is equals to t plus 1.
Okay. So what happens to y of t? Y of t is equal to t plus 1 by 2 times x of t. Is this a memory system or memoryless?
Yeah, it depends on future, but
How is it depending on the future?
t
It is
plus
not
1.
No, t plus 1 is a constant number, right? It is not. So what is, so t plus 1 is something you're giving x of t, okay, to the system, and what you are receiving is t plus 1 times x of t by 2. Okay. So if you look at your output is your output at time t is depending only on the input at time t,
Yeah,
right?
okay. So it doesn't depend on the state, but it was just a constant multiply.
Yeah, so it does not depend on the future or the past state. Hence, this is not a memory system, even this is a memoryless system.
If it is like t plus 1 by 2 into x of t plus 1.
T plus 1 by 2 into x of t plus 1, then definitely this is a memory system, because when you transmit x of t, what you receive at the output so is t plus 1 by 2 x of t plus 1. So transmitting x of t plus 1 itself is not sufficient. It is also taking the past value x of t plus it is also taking the future value x of t plus 1, right? So output at time t cannot be given just by giving the input at time t. It also needs the future value of the input x of t plus 1,
But
right?
how can we know the future value?
We don't know the future. I mean, you have to wait for it. So if you just give x of t, that itself is not sufficient to produce output at time t. But for you to get your output at time t, you have to wait for another time instant. And once x of t plus 1 is given, like uh, how do we say this? So it's like fast forwarding. Okay. So the output at time t, suppose if you do not fast forward a video at any time t, say your video is something like this, but when you play the video at 2x speed at time t, what you see is the future, right? So that is what we mean by the future. So this is maybe what you see originally at t plus 2 is visible when you fast forward a video, right? You got it, right? So you're trying to play a video. Okay. You're somewhere here. You're trying to play a video. And when you play a video originally at time t, you see some picture. Okay. Or at time t plus 1, you see a circle. When you fast forward this video, what happens is you're at the same time, you are in the same environment, but this circle will be visible to you at t. That is what we mean by output at time t is depending on the input at time t plus 1. So there are several examples like that. But if if a signal if the output signal is depending either on the past or the future, then we call such signals as memoried systems. Okay. If it depends only on the present state of the input, then such systems are called memoryless systems. Is that clear? Hello.
Yes, ma'am.
Yeah, is that okay? What about the differentiator? Did professor speak anything about differentiator in your lecture, in the memory case and memoryless case? In your lecture video?
He mentioned that the example of differentiator in system with memory topic.
Okay, he mentioned. So what did he say? Is it a memory system or memoryless system?
I don't remember exactly. The only example is mentioned. I think. Integrator and differentiator.
Okay, okay. Anyways, I'll check that. Okay, but at least for now, you can assume that this to be a memoryless system because it is depending only on the present value of the input, not on neither on the past nor on the future. Okay, for now, you can assume it to be memoryless system. Okay, right. Great. So let me go to the other next one, which is invertibility. What do we mean by invertibility? Suppose if you are given x of t, when you pass this into some system and if it produces an output y of t, invertibility implies you can pass y of t into some other system. If I call this system A, you can pass this through some other system A inverse, and if this A inverse produces you x of t, and if such an A inverse exists, then we call the system A to be invertible. Just a second. Hello, Ravi. I'm in the live session now. That's okay. That's okay. Yeah, I'll call you back once the live session is over. Yeah, thanks. Hello. Yeah. So if A inverse exists, then we call system A to be invertible. Again, examples. Um, let's take x of t into some system A which produces output y of t, where y of t is equal to x of at plus b. Okay, can you say if the system is invertible? Can you somehow retrieve x of t from x of at plus b? Can you tell me if there exists some system? We learned this, right?
Yes, ma'am.
Yeah. So if you're given x of at plus b, so what are the operations? So x of at plus b is obtained by time shifting and scaling. Shifting by b and scaling by a. So A is the system which does two operations. One is shift by b and the other one is scale by a. Okay, so that is the A system. So when you know y of t, you can come up with an A inverse system where A inverse is something that does shift by b minus b by a and then scale by 1 by a. This produces you output x of t. Hence the given system, is invertible. Okay. Likewise, there are several examples that professor taught you in class. So y of t is d by dt. So another nice property, another nice definition of invertible systems is if two inputs produce same output, then definitely the system is non-invertible. Why is this? So suppose if you have two inputs, x1 of t that produced you the output y of t, or x2 of t also produced you the output y of t. So how do you go back from y of t to either x1 of t or x2 of t? You cannot distinguish between the two signals x1 of t and x2 of t. right? So from y of t, you cannot produce back the x1 of t and x2 of t separately. Hence, if two inputs produce the same output, then the system is not invertible. Is this clear? Is this point clear? Or any questions with this point?
Yeah, ma'am.
Okay, so that's the whole idea. So suppose if you're given something like differentiator or integrator, so let my x1 of t be 1 and x2 of t be some 3. Both are constant signals but different signals. My x1 of t has an amplitude of 1. So this is my x1 of t. And my x2 of t has an amplitude of 3. So clearly these both are two different signals, right? But when you take the differentiation operator, y1 of t is equal to 0 and y2 of t is also 0. So by looking at just y of t, you cannot identify whether the transmitted signal was x1 of t or x2 of t. You cannot identify this. So hence the differentiator operator is not an invertible system. Okay. Likewise, when you have an integrator operator, minus infinity to t x of tau d tau. Okay. If suppose your transmitted signal was constant, x1 of t is same 1 and x2 of t is 3. So y1 of t would be integral minus infinity to t 1 d tau. So this, if you see, this is t plus infinity, which is infinity. And likewise, y2 of t is also infinity. So now just by looking at the output value, you cannot identify whether the transmitted signal was x1 of t or x2 of t. Okay. So hence, question mark. So you cannot identify. So hence the integrator signal is also not an invertible. So this is also a non-invertible system. Okay. So this is a non-invertible system. This is a non-invertible system. And what more? So let me take another example from your lecture notes. Y of t is x of t times x of t plus tau. Can someone say if this is an invertible system or non-invertible system? If it is a non-invertible system, can you give some example for that? Yeah. Hello.
Yeah, ma'am.
So this is a non-invertible system because let x of t is equal to u of t. Okay. And let capital T be 1. Okay. So what happens to y of t? Y of t is the multiplication of the signal u of t times u of t plus 1, which is like this. So this is u of t plus 1. When you multiply these two, what you get is u of t, right? This is u of t. Now, for the same thing, y of t is equal to x of t times x of t plus t. Let me take my x of t now to be u of t plus 1 and t equal to minus 1. So what is this? So y of t is u of t plus 1 times u of t. So this is same as the signal over here. So let me call this x2 of t, x1 of t. This is y2 of t and this is y1 of t. So this is also u of t. So y1 of t is equal to y2 of t when x1 of t is equal to u of t and x2 of t is equal to u of t plus 1, right? So for different values of t, here in this case t equal to 1, here in this case t equal to minus 1. But in any case, you can see at some point in t, these two outputs are equal for different values of input, right? So hence the signal is not an invertible system. So this is also a non-invertible system. Okay. So likewise, you can find several examples. Here I gave one such examples, but multiple inputs, if they produce the same output, then definitely the system is not an invertible system. For a system to be invertible, you should have one-to-one mapping from the output signal and the input signal. Other examples include, suppose if you take y of t is equal to cos of x of t plus c. Can you say if this is an invertible or non-invertible?
Non-invertible.
Yeah, because of the reason that cos 2 pi is equal to cos 4 pi is equal to 1. That implies whenever x of t plus c equal to either 2 pi or x of t plus c equal to 4 pi, the output is the same. Output is equal to 1. So for different values of input, the output is the same. Hence, this is a non-invertible system. Other final example that I would like to show you. So y of t is equal to t x of t plus c. Is this an invertible system or non-invertible system? Quick. Hello? Hello?
Ma'am,
Invertible or non-invertible?
invertible.
Yeah, because for every value t, we can find, for every different input, we can find a different value of output. And how? So x of t would be just y of t minus c by t. So as long as t not equal to 0, we can invert the system. But at t equal to 0, like, the system just blows up. So that is something you may have to see. So as long as t not equal to 0, we can invert this. So y of t is equal to t square times x of t plus c. Is this an invertible system or non-invertible system?
Not invertible.
So in this case, you have to look for the cases. Okay. Suppose if your x of t is equal to x of minus t, then the system is non-invertible. But if this is not the same, then the system is invertible. So this is important. So this is non-invertible only when x of t is not equal to x of minus t, and definitely for sure t not equal to 0 will be the case. You understood why I told that, right?
Ma'am, even though if this is the case, then if f of x of t is u of t, then also it is non-invertible, right?
So x of t is equal to u of t. So when x of t is u of t, what happens to, yeah, definitely it is non-invertible. Because, for all t less than 0, the signal is just C. The signal, yeah, different values of input produces the same values of output. Okay, that's true. That's correct. Okay. So this is a yeah, thanks for, the correction. So this is a non-invertible system. All right. So the later property that we can see is the stability. This is also known as Bibo stability. Bounded inputs, if they imply bounded outputs, then we say that the system is stable. Okay, which implies that suppose if you have y of t is equal to x square of t, if suppose if your input is bounded, what do we mean by bounded? The absolute value of the signal is always bounded by some value p. For example, if you have the unit signal u of t, the amplitude is always bounded by 1. So u of t is always bounded by 1. Likewise, if you take any signal, okay, so if the signal is bounded by some finite value b, if this bounded input signal produces your bounded output, if mod x of t less than b implies mod y of t is less than some b1, some other b1 value, if the output is also bounded, then we call the system is bistable. Okay, so one example that we have over here is y of t is equal to x square of t. Suppose if your x of t is bounded by b, then y of t is also bounded by b square. right? Yeah. So this is also another finite value b1. Hence, this is bibostable. Yeah. Or suppose let me take y of t is equal to integral minus t to t x of t dt. Can someone say if this is if this is stable or unstable? Hello.
Ma'am, once again, can you explain the?
Oh, okay. So if the bounded input produces you a bounded output, then the signal is known as bibostable. That's the definition. Okay, that's the property. So implies signal bounded implies if you take the signal u of t, it is bounded by value 1 because u of t can either take only 0 or 1. Hence, it is bounded above by 1. So, if any signal x of t is bounded by v, if you take this signal and if the output is also bounded by some, so if this implies output is also bounded by some other, or let me call some other value m, then we call the system is bibostable, which implies bounded input produces you bounded output. Okay, one example is suppose suppose y of t is equal to x of t square. Okay, so take any bounded input. So assume mod x of t is less than b. This implies y of t is less than b square. So this b square is b1. So mod x of t less than b implied the absolute value of the y of t is less than b1. In other words, bounded input produced bounded output. Hence, the system is bibostable. Is that okay? Hello? Is
Yes,
this
ma'am.
clear? Yeah, this is clear, right? So, question. So, is the system minus t to t, or let me call this some constant minus t0 to t0 x of t dt. Is this a bounded signal or not? Or an unbounded signal? Could you tell me?
Bounded. Bounded.
Why? Why? Suppose assume mod x of t is less than b, then it implies that integral minus t naught to t naught, where t naught is some constant, positive constant. Okay, so this dt is less than integral minus t naught to t naught b dt. Okay, so this is equal to b times t naught plus t naught, which is b times 2 t naught, which is also less than some b1 since t naught is a positive constant. Okay, hence bounded input produced bounded output. Likewise, can you tell me if this is a bounded signal?
No, ma'am.
Okay. Uh, what about this? What about this?
No, it's bounded.
Why is it bounded? So let's see. So let's take any signal x of t is less than b for all values of t. Now what happens to y of t? Y of t is less than integral 0 to t, so less than or equal to b. x of tau d tau, which is sorry, which is less than or equal to integral 0 to t b d tau, which is equal to b times t minus 0. As you can see, for t tending to infinity, y of t also tends to infinity here. Yeah,
Yes, ma'am.
correct. So as t becomes larger, y of t also blows up. So this is not bounded. Okay. But whereas if you see x of t, even as t tends to infinity, mod x of t is bounded by some constant b. But that is not what is happening with this case. As t tends to infinity, y of t also blows up. Hence, this is not a bounded signal. Is that clear? But had you had, like, if you were given that it is some constant t naught, which is not depending on t, then definitely it is a bounded signal. But if it is not a constant signal, if it depends on t, then it's an unbounded signal. Okay, that's why I wanted to show you this example. Is this clear?
Yes, ma'am.
Any questions with respect to this? You understood the idea, right? Suppose if bounded input is giving you the bounded output, the output should not be depending on t. If it depends on t, then definitely, the system blows up. As t goes to infinity, the output also goes to infinity. Yeah, is that okay?
Yes, ma'am.
So this is with respect to stability. Next, we have time invariance. So what we mean by time invariance is, you have x of t, which produces you an output y of t. Okay. Now, suppose if you delay this input, so instead of transmitting x of t, you transmit x of t minus t naught. Okay. This produces some output y1 of t. Okay. And you also delay the output. Delayed output I am representing by y tilde of t is y of t minus t naught. Okay. So if this y1 of t, which is produced by the delayed version of the input, if this is equal to y tilde of t, then we call the system is time invariant. Implies when you transmit x of t, the produced output is y of t. The implication, or at least the thought, is that if you transmit x of t minus t naught, it should produce you y of t minus t naught. But that is in general not true. We'll see such systems. In general, that is not true. If you transmit x of t minus t naught, it will not produce you the original system's delay, the original output signal's delayed version. It will produce something else. If it if if this delayed version of the input produces the original output's delayed version, which we represent by y naught, if these two are equal, then we call such a signal as time invariant. I can explain it to you guys. If it is not very clear, I can explain more, so let me know. So or let me take a minute to explain it again. So suppose you have your original system x of t. So you transmit a signal x of t, input signal, which produces you an output y of t. Okay. And now what you're doing is you're delaying the input x of t minus t naught. This produces you an output y1 of t. Okay. So if this y1 of t is equal to the delayed version of the original output signal, y of t minus t naught, then we call such a system as time invariant. It does not vary with time. If this is not equal, then we call such system as time varying system or time variant system. Okay, so let's see some examples so that it will be clear. Let's take the same differentiator. Y of t is equal to dx of t by dt. Okay, so what you have is you transmit x of t d by dt, which produces you y of t, which is d by dt of x of t. Okay, now suppose, so this is your y of t. So suppose if you delay x of t minus t naught, and if you transmit it into the differentiator, what will this be? This is d by dt x of t minus t naught, right? So let me call t minus t naught as some t prime, which implies dt is equal to dt prime. So this is nothing but d by dt prime x of t prime, right? Which is same as d by dt of x of t, right? So now let's delay the differentiated signal. So what happens here? D times x of t minus t naught by d t minus t naught, which is same as if I call this t prime dx of t prime by dt prime. Okay, so this is same as d by dt of x of t. So the delayed version of input produced some output which is equal to the delayed version of the original output. So these two are equivalent. Hence, the differentiator is a time invariant system. Okay. So to make it more clear, I'll give another example. So y of t is x of 2t minus 4. Now let's see what happens. So when you transmit x of t, what you get at the output is y of t is equal to x of 2t minus 4. Okay. So now when you transmit x of t minus t naught, what you produce at the output is y of t minus t naught. And what happens to y of t minus t naught? X of 2 times t minus t naught minus 4, which is equal to x of 2t minus 2t naught minus 4. Now try to delay the original output. When you delay the original output, what happens to it? So the original output is x of 2t minus 4. When you delay the signal original output by t naught, you see that these two are not equivalent, right? What you have is here t naught and what you see here is 2t naught. So when you delay the original output and when you see the output corresponding to the delayed input, those two are not equal. Hence, this is time variant signal or varying signal. Is this clear, or any questions I can explain to you again if you want?
Clear, ma'am.
Clear, right? So you have to see if the delayed version of input is giving you the output that is equal to the delayed version of the original output. If those two are equivalent, then we say such a system is time invariant. Okay. So I will, so since we are, running out of time, I also want to clear your quiz questions. What I'll do is I'll postpone the convolution to Wednesday's class. I'll end this summary by just saying, just talking about linear systems. So what are linear systems? Suppose if you're given some system, take the differentiator system only. Okay. So for any system, if the combined linear combination of the input, so the system that is given to you is the differentiator d by dt y of t. Okay. So suppose if the linear combination of the input, when passed through the same system, if this produces you the linear combination of the output, okay, then such a system is known as linear. Okay. Here in this example, since we took the differentiator, let's see if the differentiator is a linear system. So when we pass x1 of t through differentiator, you get d by dt of x1 of t. This is your y1 of t output. Likewise, when you pass this x2 of 3 through the differentiator, you get d by dt of x2 of t. This is your y2 of t. Now you pass the linear combination of the inputs through the differentiator. What you receive is d by dt of ax1 of t plus bx2 of t, which is equal to a times d by dt of x1 of t plus b times d by dt of x2 of t, because differentiator is linear. And this is equal to a times y1 of t plus b times y2 of t. Hence, the given system is linear. Okay? Is that all right?
Yes, ma'am.
Some other non-linear systems are, suppose you take y of t is equal to t square plus 1 times or t square x of t. Okay. So when you pass x1 of t, it produces you or t square x square of t, or we can even take x square of t. Simple example, x square of t. So when you take x1 of t, the output y1 of t is equal to x1 square of t, right? And when you take the input signal x2 of t, the output signal is y2 of t is equal to x2 square of t. Now when you take the linear combination of the inputs, what you get is ax1 of t plus bx2 of t whole square, which is equal to a square x1 square of t plus b square x2 square of t plus 2ab x1 of t x2 of t. Is this linear? Hello?
No, ma'am.
Why this is not equal to? So this is a square y1 of t plus b square y2 of t plus 2ab x1 of t x2 of t. This is not equal to a y1 of t plus b y2 of t. Hence, this is not a linear system. But can you tell me the case when this system is linear? What happens when a equal to 1, b equal to 1, x1 of t, x2 of t, their product is equal to 0 for all t. I mean, this is this is not a straight thing to see, but yeah. So if x1 of t and x2 of t are non-overlapping signals, if they do not overlap, x1 of t, x2 of t, if they do not overlap, then their product x1 of t times x2 of t is equal to 0. Notice that orthogonality is not the case, because for the orthogonality, the area of the product should be equal to 0. But what we are seeing, so this is orthogonality, but the only case that we require here is we need the product to be 0 for all values of t in order for someone to make the signal linear. So if the signals do not overlap, and like if you fix the values a, b to be 1, so for any other values of a, b, that will not work. But in general, for linearity, it should be true for all values of a, b. But if you just restrict, just giving it some dirty example. Okay, maybe we should not confuse. Sorry. All right. So yeah. So this signal in general is not a linear signal. Okay. Yeah. So that is with respect to the properties of the systems. Sorry, linear system. This is not in general a linear system. That is with respect to the properties of systems. Just revisiting them back. What we have seen today is couple of properties of the systems. We saw systems what are causal systems, so that do not depend on future, but only depends on present and past. Such signals are causal. What are memoryless systems? No future, no past, only on the present. And what are invertible systems? One-to-one mappings of the signals. If any two inputs lead to same output, then definitely they are not invertible. What are stable? Bounded input lead to bounded output. What is time invariance? Output of the delayed input, if this is equal to the delayed output, then such systems are time invariant. And what are linear? For all values of a and b, if a times x1 of t times, if this produces a times y1 of t plus b times y2 of t for all values of a and b and for all t. If this is true, then such systems are linear systems. So this is the summary. Any questions with respect to this? We can discuss convolution in the next live session. Any questions?
No, ma'am.
Okay. All right.
Ma'am, one small question which is not related to the topic. So, are we going to study frequency domain analysis in this particular course?
Yes, we will study coming in the next week's Fourier analysis and all.
Okay, actually, I remember that from our past course, the stability of system is defined upon the Bode plots.
Bode plots, yeah, those things also we'll study in the later parts of the course once we go the frequency domain representation. But for now, Bibo stability can be considered to be like this: bounded input, if it produces a bounded output, then it is called Bibo stable. Okay.
Yeah.
So we are only talking about the Bibo stability. There are other parts of stability, but we studied till this week. We studied only Bibo stability.
Yeah.
Bounded input, bounded output stability. There are other stabilities too. We can discuss them in the later weeks. Yeah. From now on, we can discuss if you have any doubts regarding your quiz topics.
Ma'am, not a specific doubt, but I would like to ask you some more practice questions, like upon this particular concept, getting the function from a graph.
Getting the function from a graph. So, as in, suppose if you're given the graphical representation of a signal.
So some more examples will be really helpful.
So, okay. Could you tell me where exactly are you facing the difficulty?
Not the difficulty, but like there will be many functions we can generate, right? 2 or 3 kinds. So like it is better to go from the options.
No, I mean, could you be more specific? Like,
Okay, for example, if there's a function like which is value which has a value 1 from 0 to x is equals to 1. So for that
uh,
particular function itself, it's a simple example. So for this particular,
fun- you mean this?
yeah, and 0 for
Huh.
all the rest of the cases.
Yeah.
So for this simple example itself, we can generate two kinds of analytical representations, right?
Uh, so you mean, okay, if you have something like this, so the question is, what kind of analytical representations are there for this signal? That's your
Yeah,
question, right?
we get two types.
Yeah, there are multiple possibilities. You can represent it using the U of t functions or rect t functions. There are multiple possibilities. In such questions, it's always better to go through the options. So
Even in U of t, many possibilities.
yeah, even in U of t, there are many possibilities. That's true. So in such cases, yeah. So there are certain questions that I have given you in your assignment problems. For example, if you're planning to write GATE exam or any competitive exams in the future, the reason they give such questions is, like, you cannot sit and solve such questions through the exam. If you want to solve them with pen paper and find out all the representations of the signal, it is going to take you more than half an hour to 1 hour. But it's in such scenarios, it is always advisable to go through the options and see what is the best option for the given question. So for you guys to have the practice only, I gave such questions where, it's good to look through the options and find the answer.
Yeah. So is there any place like where we can find some more questions? I felt that if you do some more questions, we'll get an intuition like if
uh,
shape we have to go to certain function.
Questions. So I don't have the questions right away with me, but I can prepare some questions and
Yeah,
share it with you as your next practice assignment or something. Okay.
yeah, it will be really helpful.
Yeah. But for your quiz, you don't need to worry.
Yeah,
Okay.
yeah. I guess signals and systems is a little bit easier compared to other subjects
Yeah.
because of all the explanations you have done.
Thanks. Yeah. I'll give more practice questions for such scenarios. Yeah. Any more doubts? So prepared for the quiz. Done with quiz preparation and all.
Yes, ma'am.
Great. So if yeah, so should we wait for the doubts, or do you want me to do uh, the convolution? So how would we
Better
proceed?
to keep the conversation for the Tuesday session.
Yeah, Wednesday.
Yeah, Wednesday.
Yeah, Wednesday convolution also plus the MATLAB demo I can give.
And one more
So
thing, like next week Sunday, we are having even week 6 deadline.
is it? I
Yeah,
asked them to postpone, but they told me 14th is the deadline for week 5. Is that correct?
yeah, it's for week 5 and week 6 together.
Together. Oh my God. I didn't even give them the week 6 assignments. How can they put the deadline for week 6? Week 6 assignment is not up on the portal yet, no?
No. But I'm saying in the general diploma courses case.
Ah, I see. No. I'll ask them to extend the deadline because the
Yeah, ma'am.
assignment itself is not released yet. So
It will be more useful if you can postpone it to next Wednesday.
we will postpone. We will
Yeah,
postpone because from my side itself it is delayed. So how can they expect you guys to write it quickly? No. I'll ask them to postpone. Yeah. Yeah, from here onwards, the course is going to be much challenging. So I request you guys to watch the videos properly and practice. Practice is the only thing that is required for this course. Okay. It's more and more practice. And this course is the fundamental course for your future courses. So you have to practice more in this course. Uh, uh, so Sir told certain reference textbooks, right? BP Lati. Did you guys go through those textbooks?
Yeah, ma'am. I have gone through the textbook. It's very nice, but
Yeah,
unable to
there will
find
be a
the hard
lot of
copy.
there are hard copies. Yeah, you have to purchase them. BP Lati, there will be a lot of practice problems and signals and systems by mm, Oppenheim. Let me see the spelling. Okay. Even in this textbook, you have to look through the sections that professor is teaching you. Not all sections from this textbook are being taught to you in the lecture video. So you have to look through the sections, with those sections that professor is teaching you. For example, in this book, there will be a lot of sections on discrete time signals, which is not being covered in the course. But in this textbook, look through the sections that is working on continuous time signals, and there are several exercise problems at the end of chapter. At the end of every chapter, there will be a lot of exercise problems. You can work all those problems. So nice, interesting exercise problems are available at the end of every chapter. Or MIT OCW. You know MIT OCW, right?
Yeah, ma'am.
So MIT OCW Signals and Systems course. If you go to this course, there are a lot of assignments with solutions. Okay. So I think till week 1 to 4, assignments 1, 2 may be helpful. So even those assignment problems you can go and solve. Even the solutions for those problems are available. Okay. So these are certain different textbooks that you can work with. There are also multiple textbooks on signals and systems, good books on signals and systems, which you guys can go through whatever the problem like you feel that you have seen in your lecture video. Just go and try to attack the problem. If you have any difficulty in solving the textbook problems, suppose if you are unable to solve a particular problem from the textbook, you can always email me with a photo of that problem. I can help you with that. Okay. I cannot do such things in the live session, but I can help you via email. Okay.
Yes, ma'am.
Yeah. Any other questions? If no more questions, we can end. But if you have any more questions, I can wait for some more time. I think I'm sorry. Differentiator is not a memory system. It is not a memoryless system. It is a memory system. Think I missed the point. So d by dt of x of t. So by definition, what is this? limit epsilon tending to 0, right? X of t minus x of t minus epsilon by epsilon, right? So this is the definition of differentiation. Correct? Hello, are you guys there?
Yeah, ma'am.
Yes,
Yeah.
ma'am.
So if you look the differentiator operator, this is epsilon to 0, x of t minus x of t minus epsilon by epsilon. So the output at any time t, it is also depending on the past values of the input. Hence, this is not a memoryless system. This is a memory system. Okay, correction.
Ma'am, but
Excuse
that
me.
is in
Okay.
the related neighborhood of t, right?
Mm-mm.
Limit in the sense it was just in the deleted neighborhood. It was
But
very,
still, even though the limit is very small, it's still the case, right?
yeah.
I mean, there are many such limiting values. So what do we mean by the memory system? If it requires to store another value, or if it requires to wait for another value, so how do you limit this? So as you keep going, it will be 0, 0, 1, 0.000001. So for every such value, you have to wait for another state of the input, right? So the output at any time t, it is not only depending on the input state at time t, but it is also depending on the another some state of the input. So it is taking another different state, not only this state. So that's the idea. So hence this is not a memoryless system. This is a memory system. Correction. I'm really sorry for that. This is with the problem with less preparation. You guys should not do this with your exam tomorrow. Prepare well, okay? See, even people like us, when we don't prepare and come, tend to make mistakes like this. Who pointed this? Thanks for pointing it out. Otherwise, I would have confidently told it memoryless system. Who pointed it?
Satyam, ma'am.
Thank you, Satya. Okay. Any questions? So yeah, differentiator is a memory system. Now you guys will not forget. I will also not forget something we worked it out together. Yeah.
No more doubts.
Yeah. If you guys have no more doubts, we can end the session for today. Thanks for attending. Yeah.
Thank you. Ma'am,
We'll upload this recording right away. Yeah.
yeah.
Ma'am, I have a question.
Mm.
Basically, it's a integration from minus infinity to infinity and combination of two signals with direct substitution.
A combination of two signals with
Direct delta. Multiplication of two signals.
is
I'm
this
telling
your
the no, I'm telling the exact example. Basically, it's integration minus infinity to infinity
mm,
and e to the power minus 10t into delta
mm,
in bracket 7 by 2 minus 8.5 8.5 t
aha.
bracket
Okay.
2
Could,
then
could you
dt.
could you repeat it? Delta of
7 by 2
Yeah.
minus
Yeah.
8.5
Yeah.
t,
Yeah.
then bracket close, then dt.
Okay. So, yeah, so I think I explained this kind of problems, complicated problems in one of the live sessions earlier. But, this is very simple. Though it looks very complicated, this is actually really very simple. So the only property that you have to remember while you are working with such kind of complicated problems is x of t times del of t minus t naught is always x of t naught times del of t minus t naught. Okay, so this is the only property, very, very important property, which you might be needing to solve any such complicated problem. But if you see in this problem, this is not in the form. So if you see this delta signal, it is not easily in the form of delta of t minus t naught, right? So in order to see it in the form of delta of t minus t naught, what you do is call the 7 by 2 minus 8.5 t as some t prime. Okay. Now minus 8.5 t is t prime minus 3.5 and t is nothing but t prime by minus 8.5 minus 3.5 by minus 8.5. So this is what? So this is minus t prime by 8.5, or simply so this is not in the form of delta of t minus t naught form. So call this minus 8.5 t as some t prime. Okay, so if you call minus 8.5 t as t prime, this is equal to t prime plus 3.5. Now this is in the form of del of t prime plus 3.5. This is in the form of del of t prime plus or t prime minus t naught form, where t naught equal to minus 3.5, right? So this is some form that we already know. So what you do is now make all t's as t prime. Okay, so minus 8.5 dt is equal to dt prime. Dt is minus dt prime by 8.5. Likewise, when t equal to infinity, t prime is equal to minus infinity. When t is minus infinity, t prime is equal to infinity. So interchange the integration e power minus 10 into t prime by minus 8.5 del of t prime plus 3.5 minus dt prime by 8.5. So the minus over here and the minus in the integration. So I'm interchanging the integration. That gets cancelled. So this is 10t prime by 8.5 del of t prime plus 3.5 dt prime by 8.5. Is this okay till now? Yeah.
Yes,
So,
ma'am.
so the given problem, just by interchanging the variables, calling minus 8.5 t to t prime as minus 8.5 t as some t prime, what you get is this. Now this is in the standard form. So this is minus infinity to infinity e power 10 t prime by 8.5 divided by 8.5 delta of t prime plus 3.5 dt prime. So call this some x of t prime. Okay. So now this is in the form integral minus infinity to infinity x of t prime del of t prime plus t naught dt prime. We know what happens to this. So what is this? From the property we know. So this is minus infinity to infinity x of minus t naught del of t prime plus t naught dt prime, correct? Because of the property x of t prime del of t prime minus t naught is x of t naught del of t prime minus t naught. We have here plus t naught, hence x of minus t naught del of t prime plus t naught, right? Clear? This is okay? Hello?
Yes, ma'am.
So now this term is not depending on t prime, hence I can get it out of the integration. So this is x of minus t prime minus infinity to infinity del of t prime plus t naught dt prime. We know that this is equal to 1. Hence this is equal to x of minus t naught. What is our t naught? Our t naught is 3.5. What is our x of t? E power 10 minus t naught by 8.5 divided by 8.5. This is the answer. Sorry, our t naught is 3.5. Is that okay?
Yes, ma'am.
So this is the final answer. I mean, did you face any difficulty in this? I can explain it to you again if you want. Ramit, right? Ramit only asked this question, no? Who asked me? Sorry.
Satyam.
Oh, Satyam. Yeah, Satyam. So I mean, were you not able to follow anything here?
You explain after the limit change portion.
Okay, from here you mean? From here?
Yes, ma'am. Yes, ma'am.
So till here, is this okay to you?
Yeah, ma'am.
So from here to here, it is fine, right? So what I did was replaced minus 8.5t with this t prime. Okay. So minus 8.5t in the original problem, I just replaced it with t prime. So when I take the differentiation, dt is minus dt prime by 8.5. And also when t is infinity, t prime is minus infinity because, uh, t times minus 8.5 infinity is minus infinity. Likewise, when t is minus infinity, t prime is infinity. Substituting everything back into the original problem here, in place of minus 8.5t, we have t prime plus 7 by 2, which is plus 3.5 times dt is minus dt prime by 8.5. So dt is replaced by minus 8 dt prime by 8.5. And e power minus 10t is replaced by e power minus 10 into t is nothing but t prime by minus 8.5. So t is replaced by t prime by minus 8.5. And the integration limits, when you have t to be minus infinity, t prime is infinity. So integration limits are also exchanged in correspondence with t. Okay, so this is what we have. So this is equivalent to the original problem. If I call this star, this is equal to star. Okay, so just by replacing the variables. Now, interchange the integration. When you interchange the integration, you get a negative value, right? So when you interchange the integration, so this is minus infinity to infinity times whatever is there in this double braces. Okay, and this minus gets cancelled, and that would give you integral minus infinity to infinity. This minus is cancelled. E power 10t prime by 8.5 del of t prime plus 3.5 dt prime by 8.5. Is this okay?
Yes, ma'am.
This is okay, right? Now from here onwards, what you do is, so this 8.5, I shifted to here. dt prime by 8.5. So this is nothing but integral minus infinity to infinity e power 10t prime by 8.5 divided by this 8.5 del of t prime plus 3.5 dt prime. So I just made things look little better, that's all. And this whole thing I'm calling xt prime. So my x of t prime is e power 10t prime by 8.5 by 8.5. Okay? Is that okay?
Yes, ma'am.
So now this is equivalent to integral minus infinity to infinity x of t prime del of t plus 3.5 I am writing as del of t prime plus t naught dt prime. Okay. Now, so where my t naught is equal to 3.5, or I can, to make it look more better, so let me write it like this, where my t naught is equal to minus 3.5 and x of t prime is e power 10t prime by 8.5 divided by 8.5. This is okay, right? I just wrote this like this. Is this okay?
Yes, ma'am.
Now we know that x of t prime times del of t prime minus t naught. We know that this is equal to x of t naught times del of t prime minus t naught from the properties of the delta function, right? Hence, this is equal to integral minus infinity to infinity x of t naught del of t prime minus t naught dt prime. Is this okay?
Yes, ma'am.
So this x of t naught is not depending on t prime. So this is x of t naught. So I'll get it out of the integration because integration is only for the t prime term. So this is x of t naught del of t prime minus t naught dt prime. Correct? Yeah.
Yes, ma'am.
So we can separately calculate. So this you can do as an exercise, which I think we also did it in our earlier live sessions. That integral minus infinity to infinity del of t prime minus t naught dt prime, this is equal to 1. So you can prove this is equal to 1. Okay. So if that is equal to 1, the final answer is x of t naught. And what is t naught? Minus 3, which is x of minus 3. What is our x? X is the function that is defined here, which is nothing but, t naught is 3.5 minus 3.5. So this is nothing but 10 times minus 3.5 divided by 8.5 divided by 8.5. Is this okay?
Yes, ma'am.
So that's the final answer. Okay. Okay, right? Or some confusion again?
No, ma'am. It's fine.
Yeah. So always try to, so even though the given problem is complicated, try to make it look in the standard form that we have seen. The standard form that we know is this. So always try to make it look in the standard form. Okay. Any more questions?
No, ma'am.
Yeah. If no more questions, can we end the session today for today? Yeah. So can I end the session?
Yes, ma'am.
Yeah. Thank you guys for attending. I'll ask the team to share the live session right away. Okay. Thank you so much.
Thank you.
Yeah.
Thank you.
Thank you.
Have a good day.